canonically conjugate pairs, little hij, which was spatial Riemannian 3 matrix and conjugate momenta, and then analyzed this constraint structure. And it turned out that gravity is also a first-class constraint system. It's, of course, a field theory, which means that we have to think about how to handle this in the quantum theory. I've then told you that there is a whole string of problems associated with trying to do this, certainly in the metric formulation. So, of course, you can write down classically your first-class constraints, and they generate kind of gauge transformations on your phase space, and they satisfy a correct characteristic algebra, the so-called Dirac algebra. So we had a bunch of 4 constraints, 3 momentum constraints, so-called, and 1 Hamiltonian constraint. And all of these generated transformations on phase space. And they had to vanish by virtue of being constraints. Now, the canonical quantization that builds on this formulation has formally operates with kind of wave functions that are psi of hij. But I pointed out already there that there are a few subtleties with just applying a straightforward formal kind of Schrödinger quantization where you just represent the hij hats as multiplication operators and as a conjugate momenta as differential operators. And one thing that is of kind of, you might say, blatantly obvious is that this Hamiltonian constraint has already classically such a complicated functional form in terms of these basic variables that in the quantum theory, one doesn't really know what to do with this Hamiltonian constraint equation. And I had introduced a new name for that. It was the so-called Wheeler-DeWitt equation. So Wheeler-DeWitt equation was H-perp, Hamiltonian constraint, quantized, applied on wave functions, physical wave functions, should give you 0. And there is clearly a huge problem in just trying to solve this equation because it's highly involved. The bottom line is that it has attempts to do that in the full theory have never led anywhere very particular. Now, I then started to introduce an alternative classical formulation of general relativity, which uses different variables in terms of which the 3+1 decomposed classical theory exhibits some interesting and new features. Namely, it looks, in some of its aspects, like a gauge theory, like a Young-Mills theory, associated with gauge group SO3. And I had written down these variables, and let me do it again. They consisted of canonically conjugate pairs, a connection AIA of X together with, well, one would call, if I was talking about Young-Mills theory, kind of a generalized electric field. But so here we had spatial indices. We're already sitting in the 3+1 decomposition, of course. The I and the J are spatial indices, and the A and B are internal indices. The internal indices refer to a three-dimensional space that is associated with each point X. And these are, apart from a density, dry binds. So dry binds are always these things that give you a one-to-one correspondence between tangent vectors and internal vectors of a space with a trivial flat metric. So the same holds here. But then we had also obtained these kind of connection variables, kind of gauge SOC valued gauge potentials. Now, let me write down what the first-class constraints look like in terms of these new variables. And I had already told you that we are, by going to these variables, we are introducing an additional gauge freedom, which corresponds to rotating on the internal space. That is what the little indices A and B refer to. So there one can just make also SO3 rotations. And associated with this are 3 new constraints, which I call curly GA. And their functional form looks as follows. Partial derivative I of EIA plus G Newton epsilon ABC, the structure constants of SO3, A, B, I, E, C, I, and this we can abbreviate as a curly D, I, EIA. This has to vanish. So this is a covariant derivative, right, with respect to this connection A. That's why I'm introducing this compact notation here. And this is also called the Gauss constraint or Gauss law constraint. And it's exactly of the same functional form you find when you just do a Hamiltonian analysis of a standard gauge theory. So this is what it has in common. But of course, we still have the other constraints, which are of course characteristic for gravity, not gauge theory. So this symbol Fij I had introduced to you at the end of the lecture on Friday. It is just the curvature associated with the connection A. So essentially it's dJAI antisymmetrized plus a term quadratic in the A's. Okay, I'm not writing it down here again. Contracted with an EAI equal to 0. And this is, of course, again, what we call the 3 momentum constraints. And lastly, our Hamiltonian constraint, H-perp, assumes the following functional form: 1/2 epsilon ABC Fijc divided by square root of the modulus of the determinant of this drybrine EAI EBJ minus the second term b squared plus 1 divided by, beta squared plus 1 divided by beta squared, square root of determinant EAI times EI A antisymmetrization with EJB GN AAI minus gamma IA. I say something about this in a second. And the second term of the same, that looks very similar. GAJB minus gamma JB. Now, gamma is an SO3 connection, and I'm not writing down the explicit dependence it has on E. So it just depends on this E field, because this is functionally kind of a complicated relation. SO3 connection. Now, looking at this, you would say, okay, this we know, and I certainly understand, again, the geometric meaning. Well, I know the geometric meaning of these things. What about the functional form? Now, this looks suitably easy, right? So this, of course, just depends on the A's. this is an E. So it's linear in what are natural momenta here. Okay, so that's fine. It's not too complicated, and it will be some vector fields with a straightforward interpretation again as generators of diffeomorphisms. Okay, and this is actually true. So that is relatively straightforward to check. Now this thing here consists of a quite pleasant-looking term, which is, f e squared, you'd say. Okay, maybe you have to worry about this determinant here, plus a term that looks quite horrendous, even to the untrained eye. Again, in terms of functional dependencies on basic variables. Remember, we'll have to solve kind of h perp equal to 0. Now, remember, what is this beta here? Beta was a free parameter, the so-called Barbero-Emirzi parameter, that appeared on the right-hand side of the classical Poisson brackets. And I just told you, well, it's really a free parameter, which I might choose whichever way I want, which just happens to pop up in this description. Now, if I am free to choose beta, so the argument when people first started looking at this, why not choose beta equal to I? Well, it's complex, but it's certainly a constant, which obviously makes this vanish, right? So whoops, in one go, we seem to be rid of a whole, horrendous contribution here in the Hamiltonian constraint. Now, this was what was originally done in what was loop quantum gravity initially. And then you see you had a really relatively easy looking, certainly compared to the metric formulation, form of the Hamiltonian constraint. Unfortunately, if you make this choice, then things just become intrinsically complexified, right? Because also already for the classical Poisson bracket, of course, you have a complex parameter on the right-hand side. And then, well, it turns out that kind of the reality conditions you, as a consequence, then have to impose to get back kind of to the real physics. They are such that there is no overall gain, apparently. So in recent years, one has reverted, if one discusses this constraint, to choosing something like beta equal to 1 or so. But then it clearly implies one then has also to deal with the second part of the Hamiltonian constraint. Now, the nice thing for us is, again, that this is an algebra that closes under Poisson brackets. And I'm not writing down the algebra here. Of course, if I put myself on the constraint surface where these three are satisfied, then of course the algebra is just the standard Dirac algebra we've already written down for the metric variables. Okay. Now, also briefly, right, these are 3, of course, times infinity cubed. These are also 3, and this is 1. So we have 7 first-class constraints, and of course, these we just take care of the additional kind of rotational degrees of freedom we had introduced. Okay, so algebra closes on our Poisson brackets. So what I can again attempt is a Dirac quantization now of this extended framework. Now, let us just write down a formal quantization of what we'd like to be true, well-defined relations in the quantum theory, where you're thinking of certainly a representation of these canonical commutator brackets, an A with an E commutes to delta functions. So just a translation of the classical Poisson bracket relations, now with an IH bar, and otherwise the same right-hand side as we met in the classical theory. Delta AB, delta IJ, Dirac delta of X and Y. Now, and formally, you'd think of representing now A as multiplication operators. So naturally, your wave functions now depend on this gauge potential A. AIA of X times psi of A. And the E is correspondingly represented as differential operators. H bar divided by I, 8 pi beta, del by del AJB of X acting on my wave functions, or wave functionals rather. So these psi of A's, so they live in some kind of in the auxiliary Hilbert space, where then we apply these constraints as operators to project out, hopefully, some space of physical wave functions as a subspace of this. Now, I already mentioned, so really both, you see, also both the three Gauss constraints and the diffeomorphism constraints are actually linear in E, so they're linear in these vector fields, and therefore have a transparent geometric interpretation. Now, this equation, obtained by implementing in a Dirac quantization scheme the quantized Gauss laws, this is solved by functionals that are gauge invariant. Which are invariant under local gauge transformations. So Young-Mills like transformations, gauge transformations. Now, a transformation I can, of course, label by associating a group element, little g, to every space-time point, right? And, okay, sorry, I'm using the same symbol. Please don't get confused here. So this is kind of the gauge group of local gauge transformations, SO3. So this is the space of all group SO3 valued functions. And how do they act? They act in the usual way by mapping the gauge potential to kind of the gauge transformed one, indicated by this superscript G, obtained by this action G minus 1, AI G minus G minus 1 del I G. Sometimes I should also say one actually uses SU2, because at any rate, at some stage, one is interested in coupling, say, gravity to fermions. Right? So, but that, of course, at the level of the algebra, it makes absolutely no difference. Now, the nice thing is that one knows from gauge theory already a bunch of functionals that are explicitly gauge invariant under these field transformations. And those go by the name of Wilson loops. Okay. So, and this is what we are going to look at for gravity. Functionals are the Wilson loops. And it's extremely useful to know and learn about them because they appear in lots of places when studying gauge field theories. Now, what are they? Well, they are functionals of the gauge fields that have an additional dependence on a closed curve in the underlying manifold. So what are they? Well, they are traces. I'm introducing some notation, and I'm then going to explain what the notation means. So this is a trace, right? This stands for path ordering. So it indicates that whatever stands to the right of this symbol has to be path ordered. We'll just get to what this is. And this whole object that appears under the trace is also known as a holonomy, for which I use the symbol U gamma A. That's the gauge field dependence S0 S0. Okay, I'll just draw a little picture in a second. Of the physical situation I have in mind here. Now, I've made the 3+1 decomposition, so all my fields live on spatial slices. So I can consider these spatial slices, which are called capital sigma, one at a time. Now, the situation here is, so let me look at one such slice. Now, what is a loop? I mean, abstractly speaking, it's a closed curve in the manifold, but the thing we work with is usually a parameterized loop. Right? So, which I can think of as a map from the interval, some interval with arbitrarily chosen boundary values S0 and S1 in the manifold. Now, to start with, what I'll define is a path. That's an open curve in sigma. And this can be thought of as a map, which I call little W, which somehow maps us into here with initial and final point W of S0 or S1 respectively. So and this is a continuous map, certainly, from this interval in R into sigma. Now, what is a loop? In sigma, or gamma. Now let me choose standard parameterization between 0 and 1, say And this is a map from that interval into sigma, where S is mapped onto gamma I of S in local coordinates such that gamma of 0 is equal to gamma of 1. Okay, and up here I should have written, sorry, I just left this out. It's the explicit form of the map from the interval to sigma. S is mapped onto Wi of S. Now, what good does that do for me? Now, suppose we have now such a gauge potential, and let me use this symbol A for the space of all of those. Then, in a local coordinate system, A of x, I can always just write out these components. This is, of course, a gauge potential, so it's a one form, right? So I can write this as linear coefficients. It's an arbitrary linear combination of one forms dxi. And if in addition I write then out, so this is now still algebra valued, but I haven't written the index. If I want to make this explicit, I choose just some basis in my algebra, in my gauge algebra, and let me call the generators capital X. So then this is the same as A of X bunch of algebra generators dxi. So the XA are algebra generators. Well, let me choose them in the fundamental representation. Of course, this generalizes in principle. Representation kind of the underlying Lie group, G. So in our case, that would be SO3 or SU2. And of course, yeah, so the A runs through from 1 to the dimension of the group or algebra. Okay, I hope this is entirely familiar. Now, given this object, how do I get another object that depends on A, but also on a path? Well, in a straightforward manner, in principle, by integrating this up along a path. And you see, this is a one form, so there's actually a natural pairing with an integral along, well, with a path, because integrating this, along a one-dimensional curve doesn't require any metric as an input. So I don't need a metric to be able to do this. So that's a nice thing. So in that sense, these two things are kind of dual to each other. Now, so this is, of course, already implicit, well, in my writing this year. So the holonomy being somehow the integral along A of this path. Now, there is one subtlety that comes in because of in general, the non-abelian nature of these A's. One has to give a specific ordering in which these matrices, or rather their exponentials, are going to be multiplied together. And there's just one unique way of doing this, which is indicated by this path ordering symbol. So let me just tell you what it is. So what we now mean by the holonomy of or along a path W mu of S with initial point S0 and endpoint S1 is the solution of, and now comes a differential equation, duw of S0 derivative ds is equal to a I of x dwi by ds uw of S0. So where S is just, now there's a curve parameter lying between S0 and S1. With x equal to w of S, subject to the initial condition uw of S0 is equal to E. By this I mean the unit element in the group. In the group G. Okay, full stop. Now, let us look at this equation. So we are talking about a quantity. So what have I given? I have given the path, and I've given A, capital A. So this is just defined as a field configuration. Say. Now I'm defining this object uw with free parameter S. Right? So it's a function of one variable. I'm writing down a first order differential equation for this object. And I know that solutions are unique once I fix initial conditions. And the initial condition I fixed here. So this kind of need, I define the holonomy object just as the unique solution of this equation. Yes. So here enters, of course, this algebra element, and enters the path and its parameterization. Yes?
The initial condition, the argument, should that be both S and S0?
Well, this I keep around as a dummy index, if you like. But of course, it's somewhere in the problem. Oh. Thank you. Exactly. Of course. Yes. So you see, it's a unit matrix to start with. I mean, when my path has 0 length, and then it picks up, I mean, non-trivial contributions as I move along the path W. Now what I'm looking for. Now, what you learn in the exercises is just to work with this object, yes, and to construct this UW actually as a power series in A. And I cannot emphasize that this is really kind of an important object to understand and learn how to work with, because nowadays, if you just open the archives, you will see people discussing about Wilson loops in supersymmetric gauge theories, and computing such objects for all kinds of weird shapes of loops and trying to extract, gauge invariant information, of course. So, and this is, of course, the same way we are using these in gravity. Okay, now, so these objects kind of solve curly G A hat psi equals 0. If I now think of those UWs, well, not just the UWs, but the traces as given up there as functionals of the gauge potentials. Now, it turns out that these things, the UWs themselves, they still transform non-trivially at the endpoints, but under gauge transformations. But if I then identify those two by making a closed loop and take the trace, then this is genuinely an object that is, I mean, blind to gauge transformation. So it's just a true invariant. So the idea is then to base oneself in gravity kind of on a set of functionals that already solve this part of the constraint equations. And then see, so what one then obtains, so that's what's the idea of loop quantum gravity? Is to choose Wilson loops W gamma of A. So this is just trace U gamma of A as coordinates on, well, the configuration space of this extended gauge formulation, so the one half of the phase space with respect to gauge group SU2, where I have now already factored out by this gauge freedom. Okay, so this is the idea. Instead of working, say, with the fields A and E, which are introduced up there, and their canonical commutators are introduced, I work with Wilson loop objects that already do not see kind of the gauge transformations. Of course, then my task is that in addition on this space, or rather on the cotangent bundle of this space, right, I still have to say now what do the other constraints do on this space, and how do I rewrite them, if you like, as in the quantum theory as operators operating on psi of A's, or A's where A's are already equivalence classes with respect to this group action here. So that is kind of the idea. And the idea goes back to Carlo Rovelli and Lee Smolin, who is, of course, a researcher at this institute. It's the year 1990. So here is, of course, my sigma, and now my spatial sigma. Now I have all kinds of kind of loops and associated functionals, which I want to use in constructing the canonical quantization. Now, classically, certainly already with this reformulation, as I emphasized, there's of course absolutely nothing, well, there's nothing wrong at all. I mean, it's just an equivalent way of formulating classical GR. Of course, I have to keep track at every stage of the constraints and what are the degrees of freedom. That's no problem. The point is that is now a quantization I'm going to base on these variables necessarily equivalent to what I did before. In a way, one hopes, well, it's not entirely equivalent in the sense that this reformulation may suggest new ways of quantizing this now, which now crucially involves these Wilson loops, of course, which I didn't see at all in the geometric formulation, that enable one to push this Dirac quantization program further than one could before. Yes?
I'm not sure I understand the question. Please remind
Yes.
me what the A is in the G.
Yes. Yeah, so the A, the curly capital A, I introduced somewhere here. I sneaked it in. So this is just the space. So for a fixed three-dimensional manifold, say, this is the space of all gauge potentials, SU2 gauge potentials. So that's the natural, well, it's 1/2 of the phase space in this new gauge theoretic formulation of classical GR. Okay. Now, I have various symmetry actions on these, or gauge invariances, right? One of them, and they're all kind of, in principle, they have to do with the first-class constraint structure. So on the one hand, now I have the gauge transformations, which I wrote up there, acting on the A's. And, of course, the statement being that an A and a gauge transformed A correspond to the same physics. So I want to get, again, I have a redundancy in my formulation, which I'd like to get rid of classically, and I also have to see how I handle in the quantum theory. And this, the proposal is, as usual, let me try and implement this as operator conditions on wave functions. So what I was saying is, it looks, if I now, in this extended framework, just having both the spatial diffeomorphisms and the gauge transformation, it looks as if I could relatively easily handle those because they will be translated into kind of vector fields, and I can interpret them as flows or as inducing an action on the arguments of my wave function psi of A. See, because, of course, this still carries an action under, say, the group. And what I'm saying here is getting rid of the redundancy, the gauge equivalence, psi A, psi AG. One way is to say my functionals, the functionals I'm looking at, are only functions of Wilson loops. And well, an additional argument, of course, I have to make is that I'm not losing physical information this way. But as it turns out, certainly classically, I'm not. So if I know the values, of all the Wilson loops, then I can construct uniquely, certainly for gauge group SU2, the original A, of course, only up to gauge. Right? And well, as a matter of fact, there is a high new redundancy, you could say, in going to Wilson loops, because, I come from a local function A of x. So this contains, the information about one configuration, say. And now I'm told, oh, I have to integrate these, around all possible loops. And of course, there are many, many, many loops. Of course, also infinitely many. But things now depend on a loop label rather than a point label. So you can already imagine that, well, there's a lot of redundancy in there. And that has to be taken care of, also then in the quantum theory. But as far as the gauge dependence is concerned, these are really nice, those functionals here are really nice objects on the quotient. Yeah, so that's, I hope it's now clearer. And this is to be thought of as the space of equivalent classes with respect to this action, the local gauge transformation on the gauge potentials A. Yeah.
About these Wilson loops, do we assume that they enclose a finite area or in finite area?
Well, these loops are finite. You're not saying anything, what they enclose or whether they are the boundaries of any special surfaces, no. So you just think of them as these one-dimensional integrals along one-dimensional curves. And that could be any curve to start with, right? It could also self-intersect, of course, for example. It's something I haven't drawn, but
I mean, because if we assume that they can enclose infinite area, we can use finite number of them to describe that this space is finite.
well, you might, if you're thinking of something like a Stokes theorem, perhaps at the back of your mind, yes, perhaps I can come up with a set of kind of independent loops or a small set. One has to be a little bit careful, of course, because here, this is a non-abelian situation. So already there, unlike by what I would have, say, in electromagnetism, well, one can write down a Stokes theorem, but it's much less useful because it involves, the problem is always the ordering of the A's in the loops. So yeah, I'm just alerting you to the fact that there is an additional difficulty doing this for non-abelian gauge groups. People have thought about this problem, but for this, a solution has been found in the quantum theory. So how to get rid of this redundancy for the many, in a way, of the many loops you have here. Okay, so far so good. Now, I haven't done anything that's not correct. I mean, I haven't lost any degrees of freedom. Now, what I, however, do in the quantum series, in loop quantum gravity, I make certainly a crucial assumption, which is that these kind of functionals will be represented by well-defined and finite operators in the quantum theory. So one way of thinking about this program is as follows. You recall my initial discussion about there not being kind of a unique quantization associated with a given phase space. Now, one of the ways, the practical ways one addresses this is often to say, look, I'm only interested in a limited number to start with of phase space functions whose algebra I'm interested in representing faithfully, say in the quantum theory. So that always has to be a subset, as we've learned. So because you're never able to reproduce the full Poisson bracket algebra in the quantum theory. So that's just not going to work. So here one says now, look, I'm looking at a distinguished class of functions on this quotient A, and I ask that those be represented in a well-defined manner in the quantum theory. Now, that's a non-trivial step. You don't a priori know whether that's right or leads anywhere, but this is something that's a hypothesis you can then start working with, and on this hypothesis is built all what's called loop quantum gravity. Okay, yeah, that's a question.
If you have a space that is not
contractible, yes.
Does that give rise to any special things when you use loop variables?
Yeah, then you have non-contractible loops. So then these holonomies will also carry their topological character. But of course, in general, they just contain information about the local connection, modulo gauge. So it's a more local information, but they will carry this information also, definitely. Okay, so that is a choice one is making. And it turns out that this kind of crucially then determines, well, almost everything else. Almost means almost everything but how to deal with the Hamiltonian constraint. So the choice is that one promotes now this Wilson loop. Now I should say plus kind of suitable variables that bring in a dependence on the conjugate momenta, because these only tell me about half of the phase space, namely the A's. Right? So I have to suitably add some kind of momentum variables. variables. That can be done in various ways. This has also changed kind of over time, what people consider their favorite combinations. Two well-defined finite operators in the quantum theory. How would you interpret these kind of, if you now think of them as wave functions? Well, you can think of them as having excitations, well, in terms of non-trivial kind of field contribution, only along one-dimensional lines somehow. The metric or some geometric information that is just, in a delta function-like way, could say, excited along these one-dimensional lines. So this here, it's not true. This is not what happens in the standard Young-Mills quantization. So if I am just in the Young-Mills theory, of course, it has a totally different dynamics associated with it. This is not true. These Wilson loops, they can be defined, but they tend to be highly singular objects which have to be regularized, typically, in some way. So the quantum representations one will be singling out in this way will be different from standard Young-Mills type representations. And the justification here is to say, well, look, we are after some quite different dynamics. For one thing, I still need the spatial diffeomorphisms to be factored out kind of in a similar way to what we did with the gauge transformations. And these extended objects, they certainly allow me to capture kind of non-local information under the action of the diffeomorphism group. And I'll get to that in a second. So this is a non-trivial assumption. So what does it mean? So a typical state in the quantum theory has a metric kind of excited along one-dimensional curves or graphs in sigma. Now, what turns out, or what turned out after people had looked at this for a while, it turns out that if you now look at how certain geometric operators associated with volumes, primarily 3 volumes, but also areas and length, act and are expressed in this quantum representation, it turns out one needs intersecting loops if one wants to have non-vanishing volumes, states that are associated with a non-vanishing volume, as one clearly will want to have in a physical interpretation. And that leads one to, well, structures which are intersecting graphs. And it leads one to a basis of states, which are the so-called spin network states. So this leads one to spin network states. This is just a way of labeling the arguments of a wave function psi of A, if you like. And the data that are associated with this are kind of one-dimensional intersecting graphs. In some way with kind of momentum labels, J associated with every element, with every one-dimensional kind of link or edge of the graph. Okay, so J0, J1, J2, etc. So these are spin network states. Yes, I will. So if you hear people getting excited about spin network states, this is how they arose, kind of as labeling now wave functions. So, so one can already kind of get an idea that this type of representation here will bring elements of discreteness. So one thinks now of typical wave functions as having such discrete labels here, and of operators that act on them somehow as manipulating elements of these graphs in discrete ways. And it turns out that when one now looks, say, at what the volume operator is evaluated on such functions, it's a counting formula that counts elements of graphs. And as long as these graph elements, the graph arguments, are kind of finite and depend on finite many data, then the outcome will be things like finite volumes and finite areas. So, and kind of a general discreteness that appears here in the kinematical framework, as long as I only concentrate on solving the gauge constraints and the diffeomorphism constraints. And on that level, there is a kind of a beautiful, what people call a kinematical framework, where you construct in a mathematically clean way kind of a Hilbert space, and you construct certain operators that act on the Hilbert space. Again, it's not yet the final Hilbert space because one hasn't solved the quantum Hamiltonian, the Hamiltonian constraint, but is, again, kind of an intermediate auxiliary Hilbert space. So let me just write this down as a last thing. So one has here a well-defined Hilbert space. So I call this H auxiliary prime, which consists of square integral wave functions of a quotient A over G. And now if one treats this mathematically cleanly, the way is always, one starts from a set that is dense, and then looks at the closure of this. And this is essentially a unique construction, so that's the beautiful thing of it, and gives rise to a measure d mu. And AL stands for Ashtekar and Lewandowski, who came up with this construction. So that's kind of part of the beauty of the construction. So you can certainly push your mathematical physics tools to constructing everything modulo kind of a unique Hamiltonian constraint and its solutions in such a framework. Okay, so let me stop here and leave it at that for today.